we left off, I was showing you how to calculate what we call standard deviation. So standard deviation is just a measure of variability or spread. So it gives you some idea of how spread out your data set is. And so standard deviation is always positive, and larger standard deviations mean your data set's more spread out. Smaller standard deviations means less spread out. And the example we did, we looked at the pulse rates, and it's just a number. I mean, so by itself, it's not super interesting, but the standard deviation does actually have a lot of applications. And one of the applications of the standard deviation is something called the empirical rule. And so here's what the empirical rule says. It says that if you have a data set with an approximately normal distribution, so normal meaning bell-shaped, so let's say approximately normal distribution. In other words, I'll put in here bell-shaped. So it turns out that a normal distribution can be really well explained by its mean and its standard deviation. So let's say that it has a mean equal to mu. We'll use the symbol for population mean. And say it has a standard deviation of, we'll use sigma, the population standard deviation. So if you have a normal distribution and you happen to know its mean and its standard deviation, then here's what the empirical rule says. I'm going to draw a picture. Okay. The empirical rule, so in a normal distribution, since it's symmetric, then remember the mean and the median will be pretty much the same. They'll be right in the center. Okay. So what the empirical rule, what we found is that if you look within one standard deviation of the mean, so in other words, if you go up one standard deviation and you go down one standard deviation, that within one standard deviation of the mean, you'll find approximately 68% of observations. So this is just for normal distributions in general. You'll find about 68% of us are within one standard deviation of average. Okay. So 68% of adult men are within one standard deviation of the average height. Okay. Then if you go a little further out, so say you go up 2 standard deviations and down 2 standard deviations, by the time you've gone 2 standard deviations above and below average, you will have covered approximately 95% of the normal distribution. So 95% of us are within 2 standard deviations of average. And then if you go even further, go way out. So if you go down 3 standard deviations and up 3 standard deviations, by the time you go out 3 standard deviations, you'll cover about 99.7% of all the observations in a normal distribution. So sometimes I'll call this rule the 68, 95, 99.7 rule. That's actually the way I was taught. That's what it was. I think that's the way I was taught it. But anyways, it's called the empirical rule. Empirical. So empirical means, anybody know what empirical means? Yeah, and that's right. So empirical, a good way to define empirical would be like evidence-based. It means that it was derived by observation. And so what we noticed over time with normal distributions is that if you have a data set with normal distributions and you calculate their mean, you calculate their standard deviation, these percentages hold true over many, many data sets. So it's not like theoretically true, because in theory there is no, the normal distribution is just something that you observe happening a lot in certain types of data. And so it's just something that's been calculated over time. So it's like evidence-based. Yeah. So that's why it's called the empirical rule. So this is just kind of a rule of thumb that we've observed about normal distributions over time. And it's a nice application of the standard deviation. So the thing is that if you have a data set, if you know its mean and its standard deviation, then the empirical rule tells you pretty quickly kind of the range that your data is spread over and what percentage of your data lies in a certain range. So I'll give you some examples. So everybody got that written down more or less? Okay, yeah.
Is that a plus sign? Is it mu plus 0?
Yeah, mu plus sigma. It's a sigma.
Or, yeah.
Yeah, these are all sigmas.
Sigma,
Yeah, 1 sigma, 2 sigma, 3 sigma. All right. So here's an example. So SATs, we talked about standardized tests when we were talking about shapes of distributions. So SATs are designed to produce normal distributions. And the reason they like normal distributions is because it makes inference really easy. So we know that SAT math scores have a normal distribution with a mean of 515 points, standard deviation of 114 points. So I'd like to know approximately what percentage of SAT scores are between 401 and 629. Okay. And so when you have a problem like this, where it's like a normal distribution problem, I usually just draw the normal distribution. And so we know right in the middle should be the mean. So what should be right in the middle of this distribution? 515. So everybody's going to kind of pile up right around average in terms of their SAT scores. And then you go out a few standard deviations, boom, boom, boom. And then so I do the tick marks, 3 above, 3 below. So if you're going by 114 points, so this next mark here, this would be 515 plus 114, and that would take you up to what? 629? Is that true? Okay. And then if you added another 114, that would take you up to what? 743? Is that true? Somebody should check that. I'm not feeling very confident in my mental math skills today.
Yeah.
Okay. And you go up another 114, that takes you to 857. Yeah. And then you go down. So like if you go down 114, 515 minus 114 was that 401. Go down another 114, that takes you down to 287. Go down another 114, that takes you down to 173. So the empirical rule kind of tells you sort of, and in the when you draw on the picture, it kind of quickly tells you where you see the scores of people when they take this test. So like most of the people are kind of piled up in between like 300 and 700, you know, kind of that range. You're not going to see a lot of people way out here on the top end. You're not going to see a ton of people way down in the low end. But my question is, well, what percentage is going to be between 401 and 629? Yeah, so if you go back to the rule says that within 1 standard deviation of average, which is exactly what we see here, because this is the mean minus 1 standard deviation, this is the mean plus 1 standard deviation, we should see about 68%. Yeah. Okay? So about 68% of test takers will be in that range. Yeah? Make sense? Okay. So that one's not too bad because it happens to fall right on one of the rules. So then what range of scores would it cover? Approximately 99.7%. That's also not too bad. So if the middle was 515, to cover 99.7%, how far do you have to go out? Yeah, you have to go out 3 actually, right? So you have to go out all the way up to the 3 standard deviations above and all the way up down to 3 standard deviations below. So if you're trying to cover 99.7%, then that would be scores from 173 up to 857. By the time you cover that range of scores, you're going to cover pretty much everybody who can take the test. You're almost never going to see people below 173. You're almost never going to see people above 857. Actually, I don't even know if it's possible to go over 857. I don't know what the SATs are ranked at. I don't even know how they score them anymore. They change it all the time, and I never can keep up. So, anyways, anybody here take the SATs? Yeah, your total's out of, well, I don't even know what the total's out of anymore. Yeah, I don't know. I'm not sure. It was 1,600. I think when I took it, it was like 2,100, and then they changed it to 2,400, and then they changed it back to 8. I don't know. They change it all the time. All right. How about this? Approximately what percentage of SAT scores are between 629 and 743? So I'll redraw my numbers here. Boom. I think 629 was here, right? And 743 is here. Okay, and I want to know what percentage are going to be in this range. So, what do you think it is? Or how would you go about solving it if you aren't sure what it is? What do you think? And remember, what we have to work with is 68, 95, 99.7. So what do you think? And, yeah, go ahead. Yeah, so one thing you're going to want to take, yes it is, one thing you need to take advantage of is that the normal distribution is symmetric, okay? So in a normal distribution, you have half above, half below. So like these two, the two sections in the middle are going to be identical size. And then the next bands out, those are going to be identical size, right? So where are you going from? So to make the jump from 629 to 743, you're going from 1 standard deviation above, and you're jumping up to 2 standard deviations above. So from 1 standard to 2 standard deviations, you're making a jump from 95 to 68. So you need to cover, what is that, 20, is that 27%? Okay, so to jump from 1 standard deviation out to 2 standard deviations, you need to cover 27%. But the thing is that 27% is going to be split equally between this chunk and then the chunk we actually want. So what we do then is we take that 27 and we cut it in half, and then we'll find that it's going to be about 13.5% in that range. So there's 13.5% here, and then there's also about 13.5% in that piece as well. Right? Questions about that? So you can actually use the rules. You can use the rules to find out the percentage in every single one of these little pieces of the normal distribution, basically, by using the same kind of strategy, right? Okay. So actually, and what a lot of here, I'll just add a slide here. So. Oh. So actually, if you go, if you draw the distribution here, you got boom, and you got. So if this is 68, then what has to be in either portion in the middle? 34% and 34%, right? And then we just figured out the next step. If you want to go out to 95, that means that this would have to be 13.5%, and this would also have to be 13.5%. And then what would the next pieces be? So now you're going up to 99.7. So what belongs in each of the next two pieces? What would it have to be? So you're jumping up to 99.7 from 95. So you need to cover 4.7%, but you need to split it equally on each side. So what's that, 2.35? So this would be 2.35%. This would be 2.35%. And then what's left for the tails? Not very much, right? So there's only 100 minus 99.7% left for the tails. So there's only 0.3% left for the tails. And when you cut that in half, that means there's only going to be a 0.15% left for either of the outside tails. So this is another way, like, if you're working on an empirical rule problem, you can derive them from scratch, but if you have this sort of chart on hand, then you can just figure out, okay, well, what range do I need to cover, and then you can just add up the percentages that apply to the problem that you're looking at, like on a quiz, for example. So, okay. Questions about that? And these percentages will typically hold true for pretty much any normal distribution. All right. So, The next thing I want to look at is there's another application of standard deviations. Sometimes rather than, like, for example, you could tell me, or I could tell you what I got on my SAT scores, but just telling you like my raw score on the SATs is not necessarily very informative to you. So what's another number that you'll often see reported, like if you took standardized tests in high school or if you took the SATs or ACTs, what's something else they'll tell you along with your score? Is there, or like if you ever had a kid and you go to the doctor and they get weighed and measured and stuff, they tell you their weights and measures, but they also tell you what? Let's say the percentile of that your kid's in, right? So the percentile tells you how your kid compares to other kids, basically. Or like if you take like what is Washington student? I know it's the SBAC now, right? But that's only been around for a while, and there was something before SBAC. There was WASL for a while. Yeah. Anyways, there's like standardized tests, right? They give you your score, then they give you your percentile. And your percentile is telling you how you compare to the rest of the population, basically. Okay. And so what a percentile is a percentile is what we call a measure of relative standing. And so measure of relative standing, these are values which show how you relate to the overall population. Okay, so if you're talking about babies, they measure your baby. If your baby is like if their height has a really high percentile, that means they're really tall. If there's a really low percentile, it means they're short compared to the rest of the population. Okay. If you take a test, you get a really high percentile, that means you did really well compared to your population. If you get a really low percentile, it means you did not so good compared to the general population. All right. So a percentile is a really good example of that, and we're going to actually look at percentiles here in a minute. But first, I want to show you another type of measure of relative standing that utilizes the standard deviation. Yeah. So we'll get back to percentiles. Okay, so the one I want to look at first is something called a z-score. Boom. Okay, so a z-score, what a z-score attempts to do, well, I'll give you the formula first. So if you have, so let's say that you have an observation, we'll call it x, that comes from a normal distribution. A normal distribution with, say, a mean equal mu and a standard deviation. We'll use the mu and sigma. Deviation sigma. Then we say that we call it the z-score for x. It's given by the formula. So z is equal to the observation minus the mean divided by the standard deviation. Okay. So, and then what a z-score does, okay, is for each observation, it measures how many standard deviations above or below average an observation is. How many standard deviations above or below average an observation is. Okay. So there's the formula, but down here, this is really what the z-score is trying to get at. So not only does it tell you whether someone is above or below average, but it also kind of tells you how far above or below average. Okay, so z-scores can actually be positive or negative. And if a z-score is positive, that means you're above average. If a z-score is negative, it means you're below average. Okay? So, there's a formula. That's what it is. And then we'll do some examples of how to calculate z-scores. And z-scores are also useful for comparing populations, which we'll see. So, here we'll go. If you look at the SAT example, right? So the SAT scores, they have that normal distribution. We drew it a few slides back. So let's say that you have a student who earns 580 points on their SAT math test. Is this student above average or below average? They're above average a little bit. So their z-score should be positive. So if we want to find the z-score for this student, right, we go like this. So what's the x here in this case, the observation? 580 is the x, it's the observation. The mean is 515. Standard deviation is 114. So you put this in your calculator, and you'll get, what do you get? What does it come out to be? 0.57? Yeah, if you round it to, is it even need rounded, or? Oh, it's just 0.57, perfect. 0.57, okay? So what that's telling us is telling us that a score of 580 is 0.57 standard deviations above average, right? And we know they're above average because they have a positive z-score. All right. Okay, questions on that? Make sense? How to calculate them? Okay. All right, that person is above average. You could also look at another student. Let's say you have another student. They earn a 390. Are they above average or below? Below. So we would expect that their z-score will be what? Negative. So they scored a 390. The mean was 515. Standard deviation was 114. And if you calculate that, then we get it. Negative 1.09? 0.9. So it tells us this person is 1.09 standard deviations below average. Yeah? First person was above average, slightly. Not quite one standard deviation above average. This person is actually more than one standard deviation below average. So of those two, which one of those students was further from average, and which one of them do you think would be more likely to be observed if you just randomly selected a student, right? So remember, what was the first one? The first z. So if you're exactly average, right, you would be 0 standard deviations above or below average. The first person was what? Maybe positive 0.57, and the other person was what? Negative 1.09, right? So this was a score of 390, and this was a score of, was it 580? Yeah? So which one's further from average? Yeah, so the 390 is further from average, but which one of these is more likely to be observed? Yeah, it's going to be 580. Why? They're closer to average, that's right. Yeah, so if you just look at the way the distribution is, right, where in a normal distribution, where do you have the most people piled up? Most people are piled up right at average, right? And so the closer you get to average, the more likely you are to see people in that range. So 580 is more likely to be observed, yeah, because it's closer to average. Okay, so in a normal distribution, if you have that bell shape like in SAT scores, the closer your z-score is to 0, the more likely you are to see people there. And the bigger your z-score gets out, the further you get out from average, you're less and less likely to see people with big z-scores. So big z-scores are very rare, z-scores above 2 or 3, and small z-scores are pretty common. And that coincides pretty well with, if you think about the empirical rule, right? Like the big chunk of people are right here. The 95% of people are in this range, and that's within 2 standard deviations of average. So anybody falling in this range would have a z-score between like -2 and 2, right? There's very few people that have z-scores above 2, and there's almost nobody that has z-scores above 3 in a normal distribution. It's really uncommon to see people 3 standard deviations above average. in a normal distribution. Those would be really exceptional. So, okay? All right, questions about that? Cool. The other nice thing about standard scores, and you could do this with percentiles as well, but z-scores give us a really nice way to compare people who come from different populations, but that try to measure the same thing. So like here, you know, the SAT math is one option, and we know it has normal distribution. But another standardized test that people often use for colleges admissions is the ACT. So if you look at the ACT quantitative section, the ACT quantitative section tries to measure the same thing that the SAT math measures. They're trying to measure your mathematical and reasoning skills, basically. And so the ACT is on a different scale, though. It has a normal distribution with a mean of 20 and a standard deviation of 5 points. So it's on a way smaller scale. But if you had two people who took the different tests, so say one person comes in with a 650 on the SATs, another person comes in with a 28 on the ACTs, you want to still be able to compare them, like if you want to take both of those tests as part of your admission process, right? So what you can do is you can calculate the z-score for each observation, right? So for the person who got a 650 on the SATs, we could calculate their z-score, right, by taking 650 minus 515 over, what was it, 114 was the standard deviation? Okay. What does that come out to be if you calculate that z-score? 1.008. So like 1.01 if you round to two decimals, say? Oh, okay. 1 point. I'm gonna round to two decimals. We'll see why, but typically z-scores are usually rounded to two decimal places. But anyways, so the person who took the SATs was 1.01 standard deviations above average. Is that right?
Yeah.
That doesn't seem right to me.
It's 1.8. Yeah.
I feel like that was. It says me. I was like, that can't be. It seemed close, but what was it? 1.18 if you round? Yeah. So the person who took the SATs was 1.18 standard deviations above average. That's pretty good, actually. So they definitely did a good job on their test. Then if you look at the person who got a 28, then what's going to change here is our mean and our standard deviation, right? So this person got a 28 on an exam that had an average of 20 and a standard deviation of 5. So what is that person's z-score? 1.6? Is that right? Other people get that? 1.6? 1.6. So the person who took the ACTs was 1.6 standard deviations above average. So who actually did better on their math test, basically? Yeah, right? So this is a better score. So even though they're measured on different scales, you can still compare them since they both have normal distributions. If you assume that ACT takers and SAT takers are more or less the same, then it looks like Jill did better because she was in a higher percentile. She outperformed her competition more so than Jack did. So, yep. Make sense? Okay. So the standard deviation does have some pretty decent applications. You have the empirical rule, plus you have z-scores. And we're going to actually use z-scores quite a lot in this class. So we'll see a lot of ways that we can use z-scores later on in the course. So, all right. So then we also looked at, like you guys have mentioned, we talked about percentiles. So percentiles, percentiles, they always measure what percentage of the population is at or below a observation. Okay, so if you're in the 80th percentile, you're above 80% of the population. If you're in the 10th percentile, you're only above 10% of the population. Okay, and the nice thing about percentiles is we actually already have looked at one percentile. The median is a percentile. What percentile is the median? Yeah. The median is the 50th percentile, right? And remember, what was the nice thing about the median compared to the mean? Because it's what? It's resistant to outliers, right? And so, like the median, percentiles are resistant to outliers, okay? And actually, really, I should go back a little because the standard deviation is actually not, and I should include that somewhere back here where we started talking about standard deviation. So I should include that here, okay? The standard deviation is not resistant to outliers. The standard deviation will get kind of artificially inflated when you throw in outliers. And it has to do with the way the formula is calculated. Also, remember, the standard deviation relies on the mean. So the mean itself isn't resistant to outliers, and neither is the standard deviation. So the standard deviation and the mean are really good measures as long as you're dealing with symmetric distributions. So if you got normal distributions, the mean and standard deviation are great. But not everything has a normal distribution. Not everything is symmetric. And so that's why we want to look at things like the median. And in this case, we're going to look at percentiles because percentiles, like the median, they're pretty resistant to outliers. Okay, so one way we can look at variability among populations in statistics is we look at certain percentiles. So we usually call out a few specific percentiles, which are what we call the quartiles. So the quartiles are the values that split your data into fourths, or like 25%. Okay, so the first quartile in the data set we call Q1, and it's the 25th percentile. Okay. And then technically there is a second quartile, but we already have a name for that. We just talked about it, right? The median. The median is the 50th percentile. And then if you go up another 25%, then the third quartile, we call that Q3. And that would be the 75th percentile. So the median is the middle, and then Q1 and Q3 cut the data into the other chunks, into basically fourths. Okay? And we use the quartiles in a couple ways. So we're going to see a couple ways to use the quartiles. All right, so here's an example of some data where you have some claims on collisions. So if you have in the Tri-Cities area, after you have some vehicle accidents, then people take their cars to the shop, they get fixed, and they make a claim on their insurance to cover the costs. And these were 18 claims in the area, and this is what they look like. Okay, so some of them small, some of them big. These are actually in order. So I want to show you how to find the first and third quartiles, but it's actually really easy to find quartiles because the quartiles are just, it's just like finding medians. Okay, so when you want to find the quartiles, so like Q1 and Q3, you can do that, but you actually have to start by getting the median. Okay, so if there's 18 accidents, then where's the median going to be at? Yeah, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So here's the middle of your data set, and here you have kind of have your lower half of your data set, and then you have your upper half of your data set. But there is no true median because it's an even number of observations. So then the median is just going to be the average of these two values, right? So it'd be 1657 plus 1953, and you divide by 2. I don't know what that comes out to be. 1805. Okay. So the median claim was $1,800 about. Okay. Now the way you find Q1 and Q3 is you just split your data set in half, and then Q1 is the median in the lower half, Q3 is the median of the upper half. So then down here, you go, the lower half has 9 observations. So then the median, this one will have a true median, right? Because you go 1, 2, 3, 4, boom, right? 1, 2, 3, 4. So 735 is the median of the lower 9. So that would be Q1. And then same thing for the top. 1, 2, 3, 4. There you go. Okay, so it looks like 4668 would be the median of your lower half. Okay, so then those would be your quartiles. So the lowest 25% is everything below 735. The next 25% is between 735 and 1805. And then the next 25% is 4668. And then the top 25% is above that. So, yeah? So basically it's like you get your median, you split your data in half, you got a lower half and an upper half, find the medians of those two, and then you got Q1, you got Q3. So, yeah? Any question on that? Make sense? Not too bad. All right. So, one of the tools that we use for inference with data, or it's really actually descriptive statistics, is something called the Inter-Quartile Range, which we abbreviate as the IQR. So the IQR is exactly what it sounds like. It's the range between the quartiles. So it's just Q3 minus Q1. Okay, so that's the formula. And what it is it's the range of the middle 50% of your data set. Okay. Which is kind of a measure of variability because you figure like the middle 50% of your data set is kind of like average, or those are like the common, or like that's where you'd expect to see things, is in the middle 50%. So observing the range in the middle 50% kind of makes sense. So this is what we call IQR. Yeah. So like for our data set here, right, Q1 was 735 and Q3 was, what was it, 4668. So then the IQR would just be the difference between those two. Minus 35. And then what does that come out to be? 3933. So there you go. Okay. So the middle 50% of your data has a range of about $4,000. And so by itself is not really that interesting, but the way that we often use the IQR is, we talked yesterday about outliers, and the IQR can actually help you test for outliers. That's one of the ways we use it, because we figure, okay, the IQR tells us roughly the range that the most common middle 50% observations are going to be. So then that's going to help us gauge how far up or down we should accept things. So here's the way the IQR test for outliers works, is that first you establish boundaries. So establish boundaries. Okay. And so to get your lower boundary, you're going to go from Q1 and you're going to go down 1.5 IQRs. It's always 1.5. And to get your upper boundary, you're going to go from Q3 and you're going to go up 1.5 IQRs. It's always 1.5. And then if you have any observations that are outside the bounds, any observations outside your boundaries is flagged as a potential outlier. So basically you get a lower bound and you say anything lower than that I'm going to take a look at because it looks suspicious. You get an upper bound, anything above that I'm going to take a look at because it looks kind of suspicious. Yeah? And it's nice to have tests for outliers because, like, if you're an insurance company, for example, you know that most claims that people pull that come through on insurance are legitimate, right? I mean, occasionally you might have fraudulent claims, but you don't want to have to go through every single claim when you know that most of them are legitimate claims. So if you have a good way to test for things that look unusual, it gives you a quick way to decide which claims to take a look at, right? So like we could use the IQR test or outliers to decide if any of these claims really seem unusual. So in our case, we got Q1, right? It was 735. And we got Q3, it was the 4668. And we know and we just calculated the IQR. Was it 39, 33? Yeah. Okay. So then we're going to take that, and we're going to say, okay, we'll get a lower bound by going from Q1 down 1.5 IQRs. So we're going to go from 735 minus 1.5 times 4668. And that's going to be 3933, not 46. I'm just making numbers up. 3933. And that's going to take us down to some negative value. What does that get you down to? Negative 5,164. Yeah, so 0.5. So that's fine. I mean, there's definitely nothing below that, right? We don't have anything even negative. So we're not going to have any outliers on the bottom end, it doesn't look like. So then we would go and we would get our upper bound. So we need to go from Q3 up 1.5 IQRs. So we're going to go from 4668 plus 1.5 times 3933. That'll get us our upper bound. What does that come out to be? Somewhere around 10,000 or something, I think. 10,567. Yeah, 0.5. Okay, so there's our upper bound. So now you have your lower bound, you have your upper bound. So then you just go back to your data set and you say, okay, was there anything less than my lower bound? No. But was there anything greater than my upper bound? There was, right? And so this observation right there, the 10,034 is close, but it doesn't exceed it. It's kind of out on that outer edge of what we would consider reasonable. But that 21,000 is pretty high out there. And so it looks like whatever this claim was, this should be considered a potential outlier. Okay. So, all right. Does that necessarily mean it is an outlier and we should toss it out for sure when you identify outliers? I mean, is it possible that there's something weird happened here? I mean, what could explain a really high claim value that's just way out of the normal? Yeah, right. I mean, it could have been like someone might have just bought a brand new Mercedes or something, and they drove it off the lot, and then like it was like a day old, and they smashed it. You know what I mean? Maybe it's a really expensive car or something like that, right? That costs a lot to repair. And so if the value of the car is high, then you might have really high repair value. So it could be totally legitimate, right? Or it might not be, right? I mean, there could be something weird about that. And so you might really want to investigate that and see, maybe the company was overcharging for stuff, or maybe it was just a typo. But the point is that it gives you a good idea of like, okay, that's suspicious, let's at least go take a look at it. And then you can decide after some investigation whether or not you really want to keep it or toss it out. So, all right. So, cool. What do we got? Let me see. I'll finish the rest of this tomorrow, actually. So that way, tomorrow I'll finish off the module stuff, and then I'll also bring in some practice for you guys to practice with your standard deviation. So if you want to figure out how to use your calculator to do some of this stuff, because your calculator can do mostly all of these things, like the quartiles, the mean, the standard deviation. So bring your calculators in tomorrow, whichever ones you're going to use in your exam, if you want to learn how to use those, and I'll show you how. Okay? And then we'll also finish the slides tomorrow as well.
Obviously